So I will try to do my best in a foreign language. So first, I would like to thank Paola for the invitation and Rongfu for the wonderful presentation. I think all our presentations are somehow related. This is a work between the National University, the Colegio Mayor de Antioquia, and La Universidad de Antioquia. I'm working right now finding this evidence of two-way interactions between the Amazon hydroclimatology and the tropical North Atlantic SSTs. So let's begin. This is an outline of the presentation. I'm going to talk to you about the motivation behind this work, the rationale behind this work, some Amazon tropical North Atlantic interaction that we have found from statistical measures, a physical mechanism that we are proposing to explain these interactions, some dynamical evidence that we have found, and a take-home message. So first, behind this work and behind my PhD thesis is this great notion that the Amazon is one of the major tipping points in Earth's climate. So the idea behind this is that, as we have seen in the previous talk, the Amazon has this bistability change, and we are expecting that we are getting to the savanna state, right? From the forest to the savanna state. So this change in the Amazon will therefore be a key role, a key player in the Earth's climate. We're going to change the behavior of the Amazon, and this will perturbate all the climate system. So the idea is to not see the Amazon as a simple spectator of the climate, but as a key player in the tropical climate. So first, we wanted to understand what's happening with a near region, a region near to the Amazon, and it's the tropical North Atlantic. The idea is that the tropical North Atlantic is considered as the most important source of moisture to the Amazon. So therefore, there's a connection, an important connection between those two regions. So first, we wanted to test what's going on between the Amazon and the tropical North Atlantic, and if there is another connection, a connection that goes from the Amazon to the tropical North Atlantic. We have some evidence, hydrology and surface processes over the basin can influence the weather in the region, and we have seen from the literature that, for example, the march of the intertropical convergence zone can be modulated by the convection in the Amazon, and the SSTs in the tropical North Atlantic are in some cases, for example, in El Niño years, are induced by this hydrological picture in the Amazon. So the question behind this work I'm going to present you is if the Amazon feedbacks the TNA, sea surface temperatures at seasonal and interannual timescales. So first, we took some information and we produced some data sets. The first is a data set of precipitation minus evapotranspiration in the Amazon. This data set was produced to represent the hydrology in the Amazon, the surface hydrology, and then we took also SSTs from NOAA. And with those two data sets, we start to make some computations. First, with raw data, we don't perform any transformation or any filter over the data, and then we low-pass filter the data to see if there is some changes between the seasonal and the interannual timescales. So we computed some lag CCFs between those time series. Oh, sorry. We computed average over the zones, and we also maintained the information in each one of the pixels in those regions. But with the average in the two zones, in the Amazon and the tropical North Atlantic, we performed these lagged CCFs, and in the upper panel we have the seasonal results, in the lower panel the interannual results, and for example in the upper panel we see the influence of the annual cycle. It's pretty clear. and it's because we didn't remove the annual cycle from the series. But in the second panel, in the lower one, we see that the annual cycle is removed, and we have some results that are similar to the first one. So for the negative lags, we have the influence of the tropical North Atlantic SSTs over the Amazon, and for the positive lags, we have the influence of the Amazon over the tropical North Atlantic SSTs. We see that there's a negative correlation that leads us to infer that there is a relationship between the Amazon and the tropical North Atlantic in that direction. The Amazon is capable of perturbing the tropical North Atlantic SSTs in a period from 0 to 2 months. We see pretty strong correlations when we didn't remove the annual cycle, but these correlations are not so strong, but are maintained when we remove the annual cycle. So there is a slight evidence, statistical evidence of a relationship between those two regions, and that it's a forcing from the Amazon to the tropical North Atlantic. These negative correlations can be interpreted as when we have a dry condition in the Amazon, when we have these drought periods in the Amazon, there is somewhat, there's a connection, and there will be a warmer ocean, warmer SSTs in the tropical North Atlantic Ocean. But we know that this is not a direct connection, and we have to come up with some physical mechanism. But then we perform these lagged CCFs with the average of the P-E index over the Amazon, and each one of the SSTs in the tropical North Atlantic zone that we define. And we found for the seasonal results that there is, again, this influence of the annual cycle. It's a pretty clear annual cycle here, but we found that for the lags 0, 1, and 2, positive lags, again, are related with the influence of the Amazon to the tropical North Atlantic. We see that there's a negative correlation, but a positive influence over more of the 60% of the TNA region. And there is a clear difference between the tropical North Atlantic and the tropical Atlantic. So the influence of the Amazon, it's mainly found in the tropical North Atlantic above the 5 degrees north of latitude. We found also that these correlations are about -1 to -0.75. And then we perform a similar analysis with the interannual time series. And with the interannual time series, we found strong correlations, not so strong as the previous ones, but strong enough for the 0, 1, and 2 months. So we maintain this time frame of 2 months of feedback between the two regions. And now the TNA is related to the Amazon in more than 40% of the region. So the idea behind this is that we wanted to see if there is a spatial relationship between those two regions, and if there is a clear, region in the ocean that it's responding to the changes in the Amazon. So we came up with a cartoon to understand what's happening with those two regions. And the idea is that when we have some perturbation in the precipitation or convection in the Amazon, there is a change in the surface pressure. So when we are changing, or when the surface pressure is changing in the Amazon, there is a perturbation to the surface pressure gradient between those two regions, and when the gradient is changing, the winds are always changing. So if we perturb the gradient between the two regions, the winds will get slow or get faster. But then if we perturb the winds, there will be not enough, or will be more than enough evaporative cooling in the ocean. So this evaporative cooling change in the ocean will therefore affect the SSTs. So we're taking this physical mechanism to test, but first we wanted to look for dynamical evidence that this is in the field, that this is happening in the data. So we took era interim data from 1979 to 2012, and we performed this composite analysis for the wet season and for the dry season in the Amazon, because in those two seasons we have a perturbation in convection in the Amazon. So we wanted to see if this mechanism was holding in the tropical North Atlantic. So for example, for the dry season, we have here from July to October, but now, after the presentation of Ronfu, we know that the dry season may be changing. So first in July, we see in dashed lines, we see the anomalies, negative anomalies of wind coming towards the continent. And in colors, we see the anomalies of SSTs in the tropical North Atlantic. So we see that from July to October, there is a reduction of the zonal winds directed towards the continent, and we see a gradual increase of the tropical North Atlantic SSTs. The tropical North Atlantic is lower to respond to this perturbation. We see that it takes more time for the ocean to warm up, but the winds are getting slower right from the beginning of the season. Then we did the same with the wet season. In the wet season, from November to February, we see that from November we're coming from the dry season, so the ocean is still somehow warm, but from this change, this rapid change in the seasons, we see that the zonal winds are now they have positive anomalies. So now we have a strong wind coming towards the continent from November to February, and we see how the SSTs in the tropical North Atlantic are getting colder. So we see here that there is an evidence, dynamical evidence of that mechanism is happening in the ocean. But then we took extreme events in the Amazon. So we decided to take some extreme events reported in the literature. So we took some drought years and flood years reported by Marengo and Espinosa last year, and we averaged the time series for the variables that we are using to explain this mechanism, and we somehow chase the mechanism in time. So if we have a drought year, we have this in the plot. So we have red lines for the drought years and blue lines for the flood years. And what we are seeing here is that when we start the year in January, we have precipitation way above the normal conditions in the drought years for the red lines. And then at the next month, in February, we experience a decrease in the pressure gradient between the two regions and a decrease in the zonal winds. So we're chasing the mechanism. And we see that the pressure gradient and the zonal winds are working together, are pretty, and are strong related, and they drop right now, together. And then we see in March that there is this increased SSTs in the tropical North Atlantic. So if we chase the mechanism, we're seeing that it's present in these extreme events. And when we are looking to the flooding, to the other extreme events, we see that there's the opposite behavior. So we are pretty excited with these results about the mechanism. Then we try to get rid of the ENSO. So because we know ENSO, it's a heavy forcing in this region. So we took extreme events in ENSO-related years and non-ENSO-related years. And for example, for the droughts here in the first panel, we see that the ENSO years have a pretty strong mechanism. The ENSO year has a stronger mechanism that happens even earlier. While in the other years, the non-ENSO years, we have the mechanism. It's present in the time series, but it's not so strong. And the warming of the of the tropical North Atlantic is not so strong. Also because there's some connection between the ENSO process and the tropical North Atlantic warming. That is not only explained by this mechanism. So right now, this work is still in progress. I haven't finished my PhD yet. So we have these variables that we are studying, the convection or precipitation over the Amazon, the pressure gradient between the two regions, the zonal winds, and the SSTs. But these variables are also interrelated with some other variables, like, for example, the transport of moisture from the tropical North Atlantic to the Amazon, the availability of moisture in the region, the runoff processes, the surface processes are also involved in this process, and the operation heat content might be also there involved. So we're trying to explain what's happening between those two regions with few variables, but we know that there's more things going on in here. So maybe if you have some new pieces to the puzzle, or we have some new insights that we can plug in here in this cartoon, it will be really, really great. So I'm now the take-home message. So far, our results point out the influence of the Amazon hydrology over the tropical North Atlantic. But it's not so simple that just correlate P minus E and SSTs. There's a lot going on, and it's a complex relationship between those two regions. The impact or the influence of the Amazon over the tropical North Atlantic, it's about 0 to 2 months. So we have to reduce our time scale, maybe working in pentads daily. We have to explore further this question. We know that there is the precipitation in the Amazon. It's in the form of waves, can move towards the tropical North Atlantic and be a great influence. And we have found that this relation between those two regions, and for example, for the tropical North Atlantic, is pretty strong farther north 5 degrees. So the tropical belt is not so related to the Amazon. And as suggested by these results, future anomalies in the Amazon that may include climate change, climate variability, deforestation, land use change, land use variability, might be related with future stages of the tropical North Atlantic. So including, for example, the results of that we just saw, that dry seasons tend to be more long in the Amazon, and the wet seasons are getting shorter. And for example, also the positive trend towards weather conditions in the Amazon might be influence the tropical North Atlantic. So thank you so much. If you have any question.
You are studying the connection between the Amazon and the tropical Atlantic, not the north part of the tropical Atlantic. Yes. Do you plan to study? You mentioned the El Niño years, some about that, but what about the El Niño tropical years? Have you studied that?
No, we know that there's this notion of the tropical, the Atlantic El Niño, but we haven't put this inside the analysis yet. And there's also the AMO system, the multi-decadal oscillation of the Atlantic, that we start to work on to see if there is another kind of influence in the tropical Atlantic that might be showing us I don't know, erroneous results here. So we're trying to get rid of that. I don't think it's noise, but maybe another forcings in the region.
Thank you for wonderful presentation. I'm very glad that you mentioned two mechanisms. One is through surface pressure gradient or
Yes.
lower troposphere. You actually examined that. The other is through waves, convective
Yes.
coupled Kelvin waves, and that is more deeper troposphere phenomena. I think it will be really nice as a future study to look at the relative influence of these two mechanisms.
Working together.
Yeah.
Right. Thank you.